Hi, welcome to your lesson on arithmetic sequences. This has a very strong connection to the work we've been doing recently on linear functions. Let's look for that connection in this lesson. Let's get some notes down while we watch this. There's some big key ideas coming at you soon. Okay, first of all, let's begin with general sequences. Before talking about arithmetic sequences, let's just talk about the idea of a sequence first. A sequence of numbers is a list of numbers of finite or infinite length. That means the list of numbers can be have a limit to it, or it can go forever. And they are arranged in an order that obeys a certain rule called the nth term rule. Let's take a look at what that means. So for example, we have this sequence of numbers here, 3, 6, 9, 12, 15. If this is truly a sequence, it is a list of numbers, which it is finite or infinite in this case, ... implies it goes forever. And there's some rule that creates this every number in this sequence. So let's make a mapping diagram first and then write an nth term rule. So in terms of our mapping diagram, here we are going to call this the term number, or n. So term 1, term 2, term 3, etc. We said term 1, term 2, term 3, term 4, term 5, etc. Okay, term 1 maps to the value un, u sub n, 3. Okay, so term 2, right here, is the value u sub 2 equals 6. Okay, so term number is like our input. The output is whatever the term is. So in this case, 3, 6, and then 9, and so on. So our rule is very simple in this case. U sub n equals 3n. We take every term number, we multiply by 3 to get what that term is. Okay, 1 times 3 is 3. 2 times 3, 6. 3 times 3, 9. So we take the term number, multiply by 3. Term number n multiplied by 3 gives us our number in the sequence. That's our rule. So for example, if we wanted the 20th term in this sequence, which is what asks us here, 20th term would be u sub 20, the 20th term. We would put 20 into the rule here, term number 20 times 3, and our u sub 20 must be 60. Our 20th term would be 60. Okay, here's another example. For each of these sequences, we have two sequences, we need to write down general rule. So what would be the rule for each of these? And then find the 12th term. So look at this one here. Think of this one like we did the last one.
On inverse functions. But let's begin with the...
Okay, so let's continue here. Yeah, this one. Look at this one like we did the last one. This is term 1, term 2, term 3, etc. If this is term 1 and it's a 2, and this is term 2 and it's a 4, what would you do to the term number to create each of these numbers? What would the rule be? Well, that rule is 2n. Okay, so you take the term number 1, multiply by 2 to get a value of 2. Term number 2, multiply by 2 to get 4. Term number 3, multiply by 3 to get 6. So that's the rule. Okay, now that we have the rule, find the 12th term. U12, 2 times that will be 24 in this sequence. Try that for this one as well. This one's a little different. What's going on? How can you write a UN rule for this one? So a little bit strange, right? But you do see this kind of pattern to it. The numerator is always 1. The denominator seems to be, well, this one doesn't show a denominator, but 1 is the same as 1 over 1. So the denominators actually follow the term numbers. So un equals 1 over n. Because term number 1, the denominator is 1. Term number 2, the denominator is 2. Term number 3, 3, and so on. Okay, using that rule, find the 12th term, 1/12. Okay, those are two non-arithmetic sequences, but just to get us into the idea of sequences and the notation, the u sub n and the n. Okay, so now let's jump into arithmetic sequences. This is one of two main types of sequences we're going to look at. And these are sequences with a common difference between successive terms. So very specific group of sequences. Let's take a look. These if we were looking for the next 3 terms in these, what would it be? Look at the pattern here, 9, 7, 5, 3. Okay, clearly it's going down by 2 every time, -2, -2. So 1, -1, -3. This is an arithmetic sequence because there is a common difference between every term, and that common difference is -2 in this case. So we call that the d value, -2. How about this one? Do you see the same thing happening? Yes, it is going up by 1.5 every time. Therefore, next one's 9, 10.5, and 12. So the common difference here is 1.5, up by 1.5 every time. Both of these are arithmetic sequences. Arithmetic sequences have an important property, and it's the property that connects these to our work with linear functions during this unit. So here, for example, is an arithmetic sequence 3, 7, 11, 15. We want to fill in the next term. So this is position n, term number 1, 2, 3, 4. Okay, term number 1 is 3, term number 2 is 7, and so on. What will the next three be here? 19, 23, 27. We notice a pattern of going up by 4 every time. Therefore, the d value, the common difference is 4. It's going up by 4 every time. This is an arithmetic sequence. Let's graph it. So term number 1, position n value 1 is 3. N value 2, we have a value of 7. N value 3, value of 11. Let's keep going. Notice when you line these up, if you were to draw a line through them, they are following a linear pattern. We're not drawing a line through them, however, because when we talk about sequences, they are discrete. We have discrete values. We have term 1, term 2, term 3. We don't have term number 1.5 or 2.3. So those are the values, but you can see clearly they are linear. So arithmetic sequences are always linear. They follow a linear pattern. Therefore, the rule must be something like y equals mx plus c. In this case, what's the slope? How much are we going up by every time? The common difference is like our slope. So here's 4, going up by 4, up 4 over one term, up 4 over one term. And our y-intercept in this case is -1. If you continue this one down, or think of it another way, if you took this back to term number 0, then this would go down by 4 to -1. And that's why we have a -1 here. Okay. Let's keep looking at that. In terms of sequence language, though, we're not going to write it like this, because again, this implies a continuous relationship. We're going to write it like this with u sub n and n here, because that implies this discrete relationship, discrete values producing these terms in the sequence. Okay, so arithmetic sequences, just to recap again, a sequence in which the difference between each term and its previous one remains constant is called an arithmetic sequence. The constant difference is called the common difference. Okay, so that kind of the slope of an arithmetic sequence is called its common difference, the d value. So now looking at all of these, first step, look at it and decide, is it arithmetic? If it is, what is that d value, that common difference? So first one, yes it is, d equals 2. Okay, b. Yes it is, d equals 2 again, going up by 2 every time. How about this one here? No, that is not arithmetic. This goes up by 9, then this goes up by 90, then this goes up by 900. That's not a common difference, not arithmetic. How about this one? Yes, it is. D equals -2. It's decreasing by 2 every time. How about this one? Yes, and the d value is 1/2 or 0.5. It's going up by half every time. This one here, a little bit harder to see, but it is. And the d value is -1/4. How can we see that? Well, we see a 4, 2, 4. Why don't we make this have a common denominator? If this was a 4, that means this would have to be multiplied by 2 also, both of these by 2. So you'd have a 6 here. So you'd have 7, 6, 5, and then it would be 4 over 4, which is 1. So you're subtracting 1/4 every time. Makes sense. Next one. No, it is not going up by the same amount. How about this one here? Now, all of a sudden, you don't see the terms, but you see a rule. So you're looking at this rule and you're saying, would that rule produce a sequence that's arithmetic? You could check it out by putting 1 in there, and then 2 in there, and then 3 in there, and seeing what values you get. Because once you put 1, 2, 3 in there, you're putting term 1, term 2, term 3, and you're figuring out the values. Or how about you do that? Okay, if you did that, you would notice that yes, it has a d value of 5, because the first term, if you put a 1 in here, is 7, and the second term is 12, and the third term is 17, so it's going up by 5 every time. The easier way to spot that, and we mentioned a moment ago when we graphed it, that all arithmetic sequences are linear. So if you see a rule like this, which definitely looks linear, this is linear, like y equals mx plus c, right? If it's a linear rule, it's going to be an arithmetic sequence, so yes. Okay, next one. Well, by the same logic, yes, it is, because this is clearly a linear rule with a slope of 3, and that slope is our common difference right here. Next one. Well, no. Again, you could have substituted a value of 1, 2, 3, 4 in here to see what you get. And then you would see it's not arithmetic. But again, this is not linear, so therefore not an arithmetic sequence. How about this one? Okay, maybe a little tougher to see because it's written kind of backwards, but if you wrote this 4 at the end and had this negative 0.5 n in the front, that's definitely linear. And the slope is at negative 0.5. That's our slope value. This is our y-intercept here, the 4. So again, if you plugged in 1, 2, 3 in there, you would see it works out. It's arithmetic, and there's our slope, our common difference. And last one, no way, that's quadratic. That's not linear, so not arithmetic. Okay, great. I hope you have a good grasp of what arithmetic sequences look like now. Let's take it a little bit further. With this scenario, let's apply it. Because arithmetic sequences in this course are very much about applied problems, looking for problems that follow kind of a linear pattern and using arithmetic sequences to discuss those. So here we have Pablo, who's starting a full-time job. He is given the following salary schedule that shows his annual salary for the first 5 years. You can see on year 1, this is his salary, year 2, year 3, year 4, year 5. Okay, first question. Is his annual salary increasing by a constant amount each year? If yes, then what is the common difference? Okay, so it doesn't take long to look at these numbers and realize they are going up by the same amount. This, if I take that second year salary minus the first year salary, I see 900. So that means that went up by 900. And that's clear just from these two numbers. Okay, then I take the third year salary, subtract the second year salary. I see 900 as well. So that means that went up 900. And if you continued, you'd see the same pattern. So it's going up 900 every year, his salary. Therefore, that is our constant amount, and that is our common difference of 900. Next question. Oh, and you can see the 900 there. I've noted it on there. Okay, that's our common difference. So right away we know it's a arithmetic sequence. So now this one might be a little more challenging, but let's try this out. If U1, our first term, represents his salary in year 1, so this is like our U1 value, then write his salary in years 2, 3, and 4 using U2, U3, U4. So you're going to write U2 equals something and U sub 3 equals something, but we want you to write this in terms of U1 and D. So when you write U2 equals something, it has to be U2 equals something, some numbers with U1 and D only in there. Okay, let's see what you came up with. So U2 is U1 plus D. So notice for U2, I'm writing it in terms of U1 and D. In terms of means those are the only variables here. So to get to U2, I start at the U1, the first year salary, and I add the common difference, right? To get to the second year salary, I start here and I add 900. So that makes sense. Try the same thing for U3. Okay, so for U3, we would have U1 plus what? So again, we're writing in terms of U1 and D, right? To get to the third year salary, if we begin here, what do we have to add? Well, we have to add 900 once and 900 a second time to get here. So U1 plus 2D. Okay, so try the same thing for U4 now. I think you can see the pattern now. Okay, to get to the fourth year's salary, we start at U1 and we add 900 once, twice, 3 times, so 3D, 3 times that common difference. And this brings us basically, this example with some real numbers where we see a linear growth, brings us to the idea of how we can write that in terms of arithmetic sequences, in terms of the common difference. So our general rule then for arithmetic sequences is this. U sub n, to get any future number, we take the first number and add what? How many jumps of the D value, the common difference, do we add? And look at back here. Here we are looking for U3, we did 2 jumps of D. To get to U3, we only did 900 twice, right? To get to U4, we added D 3 times. So if we go to some mystery number in the future, how many D values we can add? Well, it's n minus 1. The reason for that is this value is always 1 less than this value. You can see that here. 3 is 1 less than that. 2 is 1 less than that. And that's what we do here. This is our rule for arithmetic sequences. Okay, so now make sure you note down that rule. You've probably seen it before. Let's use it here as we continue with Pablo's story. Pablo begins this job at the age of 24. So you can see his ages here. He is curious what his salary will be when he is 65. Let's say it continues in the same kind of rule as it did in the beginning. So use this table. Okay, let's figure things out. First of all, now his age of 24 represents his first year's salary, because that's when he starts. And we know that first year of the salary, oh, let's go, that's U3. And if this is U3, how do we get U42 here? Well, let's take a look, because that's going to be essential for solving this problem. This is his first year, second year, third year. We can see from 24 to get to 65, you need to add 41 years. So that means you need to add 41 to this to get 42. Okay, so that's going to be term number 42, or his 42nd year at this job. Okay, so now we know U1, he was making 39,000, and then 39,900, and then 40,800, and so on, right? That's U1. This is U1 plus D. This is U1 plus 2D. We talked about that, right? And finally, we need a general rule for his salary then. So we just talked about that general rule for arithmetic sequences. But what rule is it going to be for his salary then? If we begin with the general arithmetic rule, like this, right? U1, the starting amount, plus some number of common differences, right? 2 common differences, or 1 or 3. So there's our rule. Rewrite this, putting in the numbers you know for this problem here. Okay, so UN, 39,000, his starting salary, plus some number of jumps of 900, because it goes up by 900. That's our common difference every year. Now we want to specifically find out what happens at age 65, right? We just figured out age 65 is U42. So U42, we put it into this rule here, that n is replaced by 42 now. And we get, if you solve this, you end up getting, I don't know if I showed, yeah, I did. Okay, so 39,000 plus 41 times 900. It's important to now take this back and understand what's happening here, right? We're using a rule, yes, a formula, but why does it work the way it does? Because again, to go from 39 to this one here, the number of jumps of 900 is going to be 1 less than the number of items, right? Because if we're going from to U3, for example, we didn't add 3 jumps of 900. We added only 2 things of 900 to get from the first year to there. So we're always adding 1 less jump of that 900 to get to a certain place. That's why this 42 becomes a 41 here. That value is 75,900. Great. Pablo's problem continues. Let's keep going. He decides to buy a car, but has to take out a bank loan to do so. Every month, the bank charges him interest. The table shows the amount that Pablo must pay each month. Okay, let's fill this table in. So here's how much he pays. He took out a loan. He pays $55 of interest that first year, and then 52 and 49 and 46, 43. So what's the difference? Well, here there's no difference. How about here? What's the difference? If this is now a sequence, these payments follow a sequence, what's the difference here? How much do they go down? Down 3. How about from here to here? Down 3 as well. Here to here, down 3, down 3. So we can see that the payments he makes follow an arithmetic sequence, because it's always going down by the same amount. So what is our common difference? -3. What is the first term? 55. So now think of it as a arithmetic sequence. Write out a general rule for that using that format. Okay, here we go. UN, some future term in this sequence, will be 55, U1 plus n minus 1 times -3, that common difference. Use your rule to find out how much interest he will pay at month 15. Okay, so we're looking for U sub 15, solve it here, and we should get this value right here. Okay, so I hope you're seeing how now things that have a common slope, like things that were discussed in a context of being linear before, are still linear, but we're looking at them now in this idea of sequences and using this formula to help us find future terms, especially in applied problems like this. All right, so the general term or nth term of an arithmetic sequence with first term U1 and common difference D is given by this formula here. We just talked about that. And n must be an element of z plus. That means n is an integer, z means integer set, and positive here, so positive integers. And we know that the n represents a term number, so we know it must be term 1, 2, 3, 4, an integer positive number. Okay, so using that formula and the knowledge we've gained so far, Find and if you're told that the first term of arithmetic sequence is 5, its common difference is 2/3, can you find the second and third terms of this sequence? And then make a rule for the nth term. Okay, so first of all, second term is u1 plus d. So u2 must be 5, which is told as u1 plus d. You can't add these fractions. You need a common denominator. So I'll change this to 15/3 here, that 5. You can definitely add those. 17/3 is u2. Follow the same logic for u3. You get 19/3. Okay, what's the expression for the nth term? The nth term formula is this. There's u1 plus n minus 1 times d. Looking for deciding whether 49/3 is a term. Well, you can put 49 into the formula. So notice here we had the formula. We replaced the un with 49/3 because we're seeing if that is one of the terms. Un is a term, right? And we're seeing if this equation works out. Because if we can solve this backwards and get an n value, then we know it is a term in the sequence. So set it equal to that. This becomes that when we subtracted the 5 here. And then I can multiply by 3, divide by 2 to get this, and that means n equals 18. So since we found a whole number for n, we know that this value is at the 18th position in the sequence. So it's part of the sequence. And finally, find the first term of this sequence that is greater than 25. We'll talk about that more later, but the answer is 32. You could, by guessing and checking, put in values into your equation and find out when it exceeds 25. I'll show you how to do that in graphing later on. Okay, here's another example of arithmetic sequence problem. We have -3, 5, ... and this sequence continues until it gets to 1,189. It says write down the common difference. So what's going on here? How much is it going down or up every time? Well, the common difference is 8. And we can see that if we do u2 minus u1, the difference between those two is 8. So there's our common difference. Find the number of terms in this sequence. Okay, so you know the sequence begins here and ends here. And that looks like the number has grown quite large. So this is sometime pretty far in the future in terms of this sequence. But you know the value of a term. You just need to know which term number that is. So why don't we use our un rule, replace un with this, and solve for n. Try it out now. Okay, so here's our rule. Our rule in this case is -3 plus n minus 1 times 8, our common difference. So there's our un rule. 1189 is replaced on this, the un on this side, and solve backwards. Solve for n. I don't know if this said, it says use your GDC, but I think we can solve, let's see. However, I'm going to pause for a second. Okay, yeah, so it says use your GDC, but you can just solve this equation backwards to get at the answer of 150. And then it mentions something about graphing again and using a table in your GDC, but we'll do that stuff in our lesson together. Okay, last thing for you to try here. It says the second term of an arithmetic sequence is 1. The seventh term is 26. Find the first term and the common difference. Okay, these kinds of problems are a little tougher, so let's work on this one together here a little bit. So again, the second term is 1, seventh term is 26. Let's take a look. So the first term, okay. Second term, if I'm writing the un rule, u2 equals u1 plus, the n here is replaced by 2 because I have a 2 here, minus 1 times d. That simplifies into the second term we know is 1, so I replace that with 1, equals u1 plus d. This becomes that. So by taking what we know about the second term and using our un rule, I was able to create this equation. This equation has 2 variables though, so we can't solve yet. Let's take the other information we're given and make another equation. So the seventh term is 26. So u7 is u1 plus 7 minus 1 times d, right? Because of this 7, this n is the 7 here. Now we can plug in what we know for u7. Seventh term is 26. I put 26 in there. and this simplifies into this. So now I have two equations with the same two unknown variables. I can kind of combine those to solve. So I take this one here, and I solve it for u1, okay, by moving the d over, so that I can take that 1 minus d and substitute it in here for u1. So there's the substitution made in here. The u1 was replaced by 1 minus d here. This allows us to have an equation in a single variable, d, so that can be solved. That's that. Solving further, we get d equals 5. So now we know the common difference. That common difference can go into any equation here, for example, here or here, and we can solve for u1. So u1 is -4, and that means if we're looking for the 100th term, we have our full rule now, u100. Here's u1, which we just found. We have our d value of 5, which we also found, and we can put 100 into the rule. So that's 491. Okay, great job. We will see you soon.